Buenos dias. Good morning. For today's video, we're going to be taking a look at controlling stepper motors. There will be several videos that I'm going to be doing on stepper motors, primarily because they're such wonderfully useful devices. The very first thing to get in your mind is, one, a stepper motor does not work like a normal DC motor, where we apply a voltage and it spins at a rotational speed relative to the voltage. Stepper motors essentially make one step of rotational movement at a time. Seems strange, but that's all they do. You energize two coils, or one coil, however you look at it. You energize these coils and it'll move to that position. Then you energize the next set of coils, then the next set of coils, and the next set of coils, and it will step one by one in a rotational motion. You repeat that very quickly, and you've got what looks like a normal DC motor. The motor is spinning around continuously. There's many different ways to control stepper motors, but the two predominant methods are to do the sequencing of that stepping by energizing those coils with a microcontroller. And then you're going to use an amplifier between the microcontroller and the stepper motor to handle the higher voltage and higher currents. Now, by today's standards, that's extremely a primitive method of controlling a stepper motor. I'm only really showing it because of the popularity of one of the drivers that are out on the market. We'll be diving into that in a moment here. So people get a lot of exposure to it, but they're inexpensive little kits that you can buy on Amazon and so forth that'll get you familiar with stepper motors and stepper drivers per se. Now, the first thing we're going to do is look at the actual breadboard and layout that I've got here on the bench. Here's our stepper motor. As you can see, the shaft is off center, so that tells you right away there's a gear reducer in between the output shaft of the motor and the output shaft of the whole unit. Imagine a motor back here, a gear drive up in this end, and then your output shaft of the whole unit. This particular one is rated at 5 volts, and because we're not limiting the current with this type of driver, we should only provide 5 volts to it so that we don't provide too much current and ruin the motor. We'll look at the data sheet for that motor in a moment. This is the ULN 2003 driver. It goes by many different names on Amazon and eBay and the internet and so forth. But essentially what it's doing is it's taking a low-level logic signal from our microcontroller, the Pico, and it allows us to direct each of these phases of the motor to current. One of the wires going to the motor is the positive voltage, and the other 4 are, so to speak, negative voltage, or the path to ground. And so what this does, this low-level signal, uses the ULN 2003 to switch each of these wires, or any combination thereof, to ground, energizing the coils in this motor. Now, there's many videos out there on YouTube about the theory of stepper motors. If you're very curious about them, I would highly recommend you look into some of those. Over here, I'm just providing 5 volts from my lab bench power supply. And then, of course, just a standard Pico here, no W. I'm not doing anything with Wi-Fi. Now, on the bench, I'm going to put this little dark colored gel over the LEDs so that they become a little bit more visible to the camera. They just seem to blow out the sensitivity of the camera. So let's take a look at the data sheet of the driver first. Or I'm sorry, the stepper motor first. I'll zoom in on this just so you get a better view. This is what it goes by, that part number usually. 5 volts, 4 phase. The gear reduction ratio is 64 to 1. The stride angle or step angle is 5.625 degrees, which also gives you 64 steps per rotation of the motor. Remember, there's a gear drive in there as well at 64 steps per rotation. So there will be a little bit of math involved in this. Now, on the ULN 2003, I've used these Darlington Pear IC chips on a number of projects now, and I really like them and I respect them. And they are very suitable for this application. But want you to be aware of something. Where it is, right here. Okay. It can handle up to 50 volts. Output current, notice maximum ratings, 500 milliamps per channel. Now we're going to look at the device just operating, okay? And then we'll come back and look at the code and try to get an explanation of what I mean by sequencing. Now, what we've got is a little magic masking tape on my motor so that we can see it rotating. Power supply is at 5 volts, and it's sitting there outputting about 0.16 amps. And it's going to go at about the fastest I can make this one go. And you'll see that's the motor rotating. It'll only make 1 revolution. And over here, you probably can kind of see maybe some waviness to the lights as their LEDs are representing which coil is being activated and deactivated. So you'll kind of get an idea what's going on there. But this is exactly what a stepper motor does. It allows us to rotate it, controlling the velocity by controlling the rate of steps we allow it to make. It can only go so fast, like a regular DC motor. Generally, you'll find a much lower performance level. For characteristics, stepper motors provide the most torque at idle, and then it continuously goes down the faster you move it. So keep that in mind. Whereas DC motors, you can maintain a decent amount of current and torque through most or much of its RPM range. Definitely stepper motors go down very rapidly. Now what I want to do is slow this way down. I am going to change, I'll explain this in more detail in a moment. I'm going to change that to about, I think that'll be about 10 milliseconds between each step. So it's going to go much slower. And what I want you to see, okay, we can see the sequence flashing up above here, and you'll notice that the motor's going slower. Now, all those signals to make this happen, of course, are coming from the Pico. Now I'm going to slow it down even more. Let's go even more. Bear with me. And we'll go a little bit more yet. Sorry about that. But what I want you to do is see the sequencing process of, okay, now you're almost able to see it. It's going much slower. Look at how slow the motor is going now. I'll stop it. I'm going to slow it down even more. Okay, now you'll see it's going from 1, 2, 3, 4, stepping across, energizing the coils as needed to get this motor to go 1 step at a time. And as you can see here, it's going incredibly slow, but it's also got a lot of torque at that low speed. The faster we make this go, the lower the torque gets. Now, why do I refer to this as sequencing? The Pico is providing the order in which these coils are energized. So we're setting that sequence to energize the coils in a specific order to make it go forward which I will stop it right now, and I'm going to speed it back up again. And this time I'm going to set it in reverse rotation. And now I've changed the sequence of those lights going on and off, which represent the coils being energized, and the motor goes the opposite direction. We'll do that one more time. It's going clockwise. If I change that order by setting that variable, it'll now goes counterclockwise or anti-clockwise for the rest of you people in the world. So that's, in a nutshell, in a very brief nutshell, the sequencing of a stepper motor. If you mix up that order, it will not work correctly. We will do a quick demonstration here. What I'm going to do, I'm going to switch a couple of wires. I'm going to take these two wires and flip them. So that's one of the coils. Give it back some power again. And you'll notice that the motor won't even run this time. It's just sitting there vibrating. It's vibrating very fast because the coils aren't being energized in the correct sequence for it to move rotationally. So I'll switch those wires back, and we'll be back to having a working stepper motor. Generally, having the wires cross like this, as long as you're within one coil, won't really hurt anything. And sometimes you actually have to experiment with them on motors that you don't have specifications for. And now we're back to working when it's all wired up properly. Imagine that. You wired up correctly and it works. Now let's take a deeper dive into the code. One of the things I may have missed on my ongoing series for the Thani editor was enlarging and reducing the font. Probably one of the biggest complaints and most consistent complaints I get from you folks. And I understand. I too watch programming videos, and if I can't read it on screen, it's very annoying. If you hold down the control key and rotate or roll your mouse thumb wheel or wheel, you can enlarge it. And I think that's actually what's been happening in some of the videos. If my hand is over here and I'm touching that control and I do a scroll, instead of scrolling, I shrink the font and I'm not paying attention. But nonetheless, I'm going to do better to try to keep that font large enough so that you can see it. Hopefully this size will work for you. We're going to start out in this area of the code, the comments. And this often helps a lot of the viewers understand the math and some of the information that we're presenting. In this case, I'm just giving you a source for the ULN 203 APG module. Again, it goes by that other part number 2. I'll include that in the comments, which are, I think that's the other number right here, where you find it on Amazon. Now, calculating the steps per revolution at the output shaft. Now, keep in mind, this particular stepper motor is both a motor and a gear reducer, or a gear increase, speed increaser, depending on how you look at it. So you have to keep those two things separate and then combine them at the very end for the output shaft. The first thing we're going to look at is the motor itself, and that's a 5.625 degree step. For every step that we make it move, that's how far the motor's going to rotate, and that's per step. If we take 360 degrees and divide that by that step angle, we're going to get 64 steps, and that's per revolution of the motor. The gear ratio is 1 to 64, or 64 to 1, depending on how you want to look at it. That means there's 64 steps per revolution times the gear rate, 64, which is our gear ratio, and that equals 4,096 steps for one complete rotation of the output shaft. Very important. So that's where we're factoring in the gear ratio. Now your total resolution at the output shaft would be 360 degrees, one rotation, divided by 4,096 steps, and that equals 0.08789 degrees. A very tall, very small rotational amount of movement at the output shaft. Now the maximum RPM I got with testing on this particular motor, driver, and power supply. The fastest I could get from testing was the shortest dwell time between steps was 800 microseconds, which is 0.8 milliseconds. So if I take 1 divided by 0.0008, that equals 1,250 steps per second. 1,250 steps per second times 60 seconds equals 75,000 steps per minute. If we take the steps per minute divided by the steps per revolution, that will give us our fastest possible RPM, 18.31 revolutions per minute. Now, of course, you got to factor in a little bit here, because down below in our loop, there's other code that's causing delay in here as well, besides our speed limiter, which is this dwell. So it'll get you close calculation, but nonetheless, you're going to need to understand this in any of your designs using stepper motors. The math is quite simple if you just take it through step by step. There are no external libraries needed to run a stepper motor, but we do need to import machine library to gain access to the pins, and the time library to get our microsecond resolutions sleep function. We're going to create an output for each of the 4 coils, and I'm just calling them C1, C2, C3, C4, and our machine.pin I'm using on the Pico GPIO pin 1, 2, 3, and 4. And we're going to go into a fritzing diagram here in a moment, so that'll help make that a little bit more clear. And we're setting those pins as outputs. So now let's look at this in the fritzing diagram. Here I'm using a battery pack to indicate power going into our circuit board, our driver module. Here's our stepper motor over here, and we're looking at the belly of it, just as it is on the workbench. Here are the 4 wires going back to the Pico. I'm going to zoom in on that. Now, GPIO pin, or physical pin number 1 is GPIO 0. I wanted to start with 1, and I'm going to move this wire so you see how they're marked. That one's in 1, in 2, in 3, in 4, in 5, etc. So that way the wiring could not be simpler. GPIO 1 goes to in 1, GPIO 2 goes to in 2, 3 to 3, and 4 to 4. That's all there is for the wiring on this. It's quite simple. Not a whole lot that you can goof up on it. If you do goof up on it, the motor won't rotate. It'll just sit there and vibrate. Maybe if you got good hearing, you'll actually be able to hear the whining noise that it makes. So let's get back to the code. Now here I'm saying this would be your GPIO pin, and connect that to in 1 on the module, matching exactly what we just described. Now we're going to look at this function, and while there's a lot of code in it, it's really quite simple in nature. We're going to need a global variable phase pointer, and we're going to set that to 0, as in we're pointing to nothing at this point, because we haven't energized any of the coils on the motor yet. And I'm keeping it global so that I can show that information down here while I'm doing debugging, and I want to observe the flow through all these decisions here. We're going to pass into this a direction variable that'll either be 1 or -1. That'll allow this sequence of setting the coils to either run forward or backward. Very simple process. our phase pointer is equal to the phase pointer plus the direction. So whatever this currently is, we'll add this to it. And it'll either get bigger if we're giving it a +1 on direction, or it'll get smaller if it's a -1 from the direction variable. Now we got to roll over because we can only sequence our positions 1 through 8. And we'll look at that here in a moment. But if it can only go 1 through 8, we've got to handle that rollover. So if the phase pointer is less than 1, i.e. 0, we want to set it to 8 because it'd go 1 to 8. If we're greater than 8, well, the next logical step in our loop would be to get it back to 1, making sure everything is 1 through 8. Now, depending on the sequence phase desired, and this phasing you can often, this will work for most stepper motors, but you'll even see this listed on some data sheets for the motors or for drivers. But you'll see the sequence, and this would represent pin 1, 2, 3, and 4, and how we're energizing them. So that would be off, 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 and on. And if phase pointer is equal to 1, we would set the sequence of energized coils this way. And so here is C1, coil 1, setting the value to off, 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 and then number 4 is on. Now, to make the motor move in the next direction, we would have to change the sequence from this to this. So now if next time that this is called, the pointer would be incremented by 1, and our phase pointer would equal to 2, so to speak. Our sequence that we now need is 0, 0, 1, 1, off, off, on. So coil 1 off, coil 2 off, coil 3 on, coil 4 on. Next one, next time this is called, it'll jump to the next pointer. We need our sequence to be 0, 0, 1, 0. Coil 1, 0, coil 2, 0, coil 3, 1, coil 4, 0. See a pattern here? And if you look at this, it just is a flowing of turning on 1 or 2 channels or outputs, and then that's just moving from left to right. Now we get to the end, we come back to the beginning. When we're running with a negative direction value, it's actually going backwards through this decision-making list. And when it's positive, we're going from the bottom, lowest number, up to the highest number. And that establishes the stepping or the coil energizing sequence to make the motor step properly. If you do this stepping out of sequence, the motor can't run. It'll just sit there and vibrate, or you might get erratic rotations out of it. So this is very critical to making a stepper motor run. Now we're down in the main logic, or the main control loop, the endless loop, or in our case, a loop that ends. We're going to set a step counter, and we'll set that to 0. And while that counter is less than 4096, which we want to run for 1 full revolution, that calculation was up here. So that is 1 revolution at the output shaft. We'll increment our counter by 1. We're going to tell the device which direction we want to go. 1 for counterclockwise, -1 for clockwise. And then we're going to sleep for 800 microseconds. And then that loop will just keep repeating. This variable right here, or this amount, is what controls the rotational speed. So we'll go ahead and run this again, and you'll see that's as fast as this little motor can go. Now let's try to make it run much faster. I'll try to double that speed by cutting the microseconds, the delay time between each step, to 400 microseconds. We'll run it, and you think it'll go twice as fast? Nothing's happening. The motor's just sitting there vibrating. It can't switch that fast. And that's very common for a lot of stepper motors. They have a max RPM that they can run at. And when they can't achieve that, they just sit there and vibrate. So now we'll slow it down a lot like we did earlier. So I'm going to increase that dwell time between each step, and we'll take it up to 10.8 milliseconds. And we'll run that, and now you'll see it's going much slower, and of course the sequencing is going much slower as well. Now you might recall at the beginning of this video I was really kind of suggesting that this isn't the best way to drive a stepper motor. There's a couple of reasons for that. One, this sequencing process we have very little control over. You might not understand how important that is yet, but all we can do is make this motor that's in here move one step at a time. With some fancier sequencing and some other tricks, we might be able to get it to move a half a step at a time, but it's still very coarse and crude. This particular module, you should be providing it with the voltage that the motor is rated at, 5. Now it's very common to run stepper motors at much higher voltages, but when you do, you have to limit the current going into the motor. Otherwise you'll, well, you won't let the magic smoke out, but you'll ruin the motor and probably fry it. So those are a couple of the limitations. And then probably the most important one is pure performance. Whether it's rotational speed, smoothness, quietness, all things combined, modern stepper driver modules are far superior to doing this primitive form of sequencing. Now I'm just going to put another motor here. Let's move all this over. Oh, there it is. Okay, now that'll give you kind of an idea of a size difference between the two. This is only a NEMA 34 stepper motor. There's bigger. They go up into the 40 series, and then there's double stacks, triple stacks, etc. But this is a very powerful stepper motor, and it requires 4 amps of current, which means this sequencing driver only handling a maximum of a half an amp simply isn't going to cut it. And this one in particular is 8-wire, but we can make it work with this sequencer with some careful wiring. But we can't drive it at full current with this connection or combination, and I can't do what's called microstepping. Microstepping is the ability to take each individual step of the motor and divide that into smaller steps, yet by only partially energizing one side of the coil or one coil versus the other. That allows you to have much higher resolution and actually much better performance. Your accelerations and decelerations tend to be much smoother, and you have less, I'm going to use the wrong term here, I'm going to call it hysteresis, but that's not what I'm looking for, where the motor actually goes into a spaz state. It just sits there and vibrates because it can't accelerate or move fast enough. And those other modern day drivers handle a lot of that, and you get much better performance out of them. Plus, you can usually set the output current in that module or on that module so that you can control and limit the current going into the motor so you don't ruin it. Now, I've been messing around with stepper drives, stepper motors. I've even created my own primitive ones and so forth. But a lot of my experience comes from the industrial world or industrial type applications. So performance is truly king. Another area that you're seeing immense improvements in performance or utilization of improvements is 3D printers, such as, let me see if I can get you over here. 3D printers, these guys, they are very noisy if you've got low performing stepper drives in them. You get the quiet drives, and the motors are near silent, which is wonderful if you're sitting next to one, such as I do here. So even with small motors, big motors, and everything in between, the industrial world has really pulled forward tremendous capability out of stepper motors as an economical means of creating motion. Now, I don't want you to not experiment with this system. It's a great tool to experiment with and learn more about stepper motors. But I want you to be very cautious and careful to understand that these are very limited in performance and capability. Now, in a future video, or videos for that matter, we're going to be looking at other stepper drives and stepper systems. We're going to be taking a look at what's called a step indirection or a pulse indirection stepper drive, several of them. But I'll be explaining their application and so forth within Thani as we do here on the bench. I have also got a video coming up about my CNC router, where I recently put on a closed loop system of control for that. They're closed loop steppers and drives, so you get even greater performance, greater reliability out of it at a slightly higher cost. But for what I'm doing on my CNC router, it is a very worthwhile investment, I think. So without getting into yet another hour-long discussion on all the aspects of stepper motors, I think I'm going to wrap up this video here at this time. Hopefully you've gained some insight into these neat little guys, and I sure would appreciate it if you guys could like, share, subscribe, tell others about this channel. I could certainly use the help. More subscribers and viewers I get, the more I can fund more of these videos, and we can have a lot more fun with all of it. Good to see you again. Thanks for watching. See you in the next video.